This is the ELTE260 Module D video lecture. Here are your activities. Download the lecture, and then you can click on this link here, the lecture video, to watch what you're listening to right now. You're going to pause the video to follow other links from the PowerPoint when prompted. Fill out the lecture video worksheet. Complete the I/O connection sheets. Turn in a completed lecture video worksheet. Here's our outcomes. Why should a stop push button be wired normally closed in a motor starting circuit? Why is it dangerous to use an internal bit for motor starting memory? The lab has an activity for this. How should the motor starter auxiliary contact be wired and programmed in a motor starting circuit? We talked about this last week. We'll do some more with the lab. How should the motor starter overload contact be wired and programmed in a motor starting program? How are internal bits addressed? Explain the steps needed to perform an online edit. Explain the difference between volatile and non-volatile memory. Explain how a SLC 500 scan works. We're going to look a little bit more in depth into that. Let's start with our Module C review. Quizzes, you should have got a quiz back, and if you have any questions, ask the professor about that. Are you still having connection problems? So we did sourcing and thinking last week, and you should know that we were grounding out our output modules, and we were bringing voltage to our, grounding out our input modules and bringing voltage to our output modules because we were syncing input modules and sourcing output modules. Still having configuration issues? You should be able to make RS links connections and then start your program and configure it. Some people were having problems with this right here because they were doing their program and they were addressing, and then they were getting errors because there was no input or output cards installed or configured, and they just typed the inputs instead of dragging them, and they weren't there. And once again, AC will ruin a DC proximity switch. If you run AC to a DC device, you're probably going to get a fire. If you run DC to AC, it probably just won't work, but you got to know the difference between your voltages. So we did a Jeopardy example at the end. We had some interesting issues here that usually people try and want to wire up the logic. They want to show ladder logic wired into the input modules. That's not true. The logic is all performed on the program. It's all fictional. All you have to do is wire the push button, a single push button, into a terminal, the next push button into the next terminal, and so on. Same with the outputs. And so there's the Jeopardy solution right here. And take a look at it, and you shouldn't be wiring in a relay, and you shouldn't be wiring up any logic. So take a look at the Jeopardy solution. The I/O module descriptions, to remind you, the different I/O devices are in your handouts. There's AC or DC, we talked about. Solid state or relay, that's no moving parts. The benefit of the relay was it can switch either voltages, and it has a little bit more ampacity. We talked about voltage and neutral commons, so whether it was the hot and the neutral, or the plus DC and the minus DC. We talked about the number of points, so a lot of our cards are 16 bits, so the output modules might have 2 voltage taps, 8 bits per voltage tap. We talked about ampacity per bit, so on the output modules, those were looking like a ½ an amp or less, and so we need to use interposing relay to turn on big things. Ampacity per card, the whole card, all 16 bits we looked at, was about 8 amps. So those solid state cards don't handle a lot of amps running through them. And then the switching threshold was you need some voltage coming through there. If you get a little bit of voltage, it might signal the card. We're going to look at that in the lab this time, but you definitely want to be sure that you get the right voltage, so you're not just hitting the threshold, you are getting a true signal instead of just something that activates the card. giving you a false signal. Talk about a syncing input module here. Syncing was neutral run to common. That's the way it was synced. And then these sensors have to deliver voltage. So if you had a solid state sensor here, it would be a PNP. Remember, input modules could be sourced, but we don't do that. We run the neutral or the negative to the input module. The sourcing output modules, what we do is we run voltage here, hot to the card, or voltage to the card. And then each one of the bits then delivers voltage. This one here shows the interposing relay that we talked about. This relay can turn on it doesn't take many amps to fire this coil, maybe half an amp, which is what this is rated for, or less. And that closes a switch, and this circuit over here can be very heavy duty with a high ampacity, and it won't affect or burn out the card. We did test modes versus forcing. Test disabled all the outputs. The test showed your logic being true. It was solving your logic for you, which is useful to see if your logic, if you were thinking like you should, so you could simulate your ladder, but it actually didn't fire the outputs. Forcing, on the other hand, is often used to turn on output. It overrides the ladder logic, so that you don't have to have everything true in the ladder. You just want to check and be sure that something's working. You want to be very careful on this. It's very dangerous because if you turn something on, it's going to override the logic. In this case, are often the safeties, and then it's going to possibly hurt somebody. And forcing can be used to also disable an output. So maybe that's similar to the testing, except testing disables all of the outputs. Maybe you just want to disable one of the outputs, the most dangerous one, but you would like, all the lights and everything else and all the enunciators to work, just not maybe the main motor. So you could use forcing to disable an output as well as enable an output. We talked about solid state. They're solid state. They don't have any moving parts. Traditionally, the switching mechanism for AC would be triacs, and the switching device would be for DC would be transistors. And if you run too much ampacity through these, you will blow these up. We talked about the optical isolation. That's what each one of these provides. They turn on an LED. There's a sensor on the other side of the LED that closes the switch. So there's optical isolation with these triacs here. Solid state sensors. PNP is producing voltage, and they get wired into a syncing module. If for some reason we wired a sourcing input module, we would need an NPN, but we're not using that. We talked about the pinout of cables, so I gave you a prox, and it was a 3-wire. Remember, this here is a picture of the prox. So you're looking at the bottom of the prox. You got 1 on the left, 3 on the right. The cable is the mirror image of this. So if you need to fluke this out, it's going to be opposite of this. This would be the right side of the cable if you were looking at it, and then you would run your fluke to the other end of the cable, and you'd look for the beep or the continuity. So sometimes people forget that they're looking at the mirror image. This is not the cable. This is the prox. The cable's the mirror image. We talked about how you can jump a common to do an input. You can't do that with an output. Brown, black, blue, we talked about the wires. So the voltage here going to 1 was brown. The negative here was blue. And then this square device here is your sunk input module. How do I know that? Because this module has a wire here running to negative, which means that it is sunk. And therefore, the black wire here, number 4, is a PNP. It brings voltage into the input module. So voltage in the input module, and then it goes to negative. AC and DC components. We had some confusion about wiring up the AC and the DC voltage. You can have both. You can have AC inputs and AC outputs, and DC inputs and DC outputs, and you can have multiple modules of each. And the main thing you want to do is you want to keep your power supplies separate so you know what is going on. Don't run AC into the DC output module. Here's a video of your link on here, and follow along your worksheet to get a little more practice of sourcing and syncing. On the PLC programs, what you need to be turning in is your documentation. So you want to do an IO map legend, and so this is your address, I:1/1 versus a description. Maybe that is PB1 or proximity 1. So your IO map and your legend is your description. You want to have your ladder logic documented. So for that input, I1/1, for example, you want to label it as PB1. And then you want to label the rungs or a group of rungs if they're performing an operation, such as these rungs, next 4 rungs blink a light, you would label that. That would be really useful for somebody who was troubleshooting. And then you're going to turn in a wiring diagram. Once again, the wiring diagram shows the source and the sink, and it shows the actual symbols. So this shows the NEMA ANSI symbols. If it's got a push button, 1 PB. If it's got a contactor or a relay or a solenoid, 1 SOL, the wiring diagram is going to show where those connections are made. Once again, used for troubleshooting. Use the data table for addressing. I already stated that some people just went ahead and typed, I:1/1, but they actually had set up an input module in the configuration, so it gave them an error. If you use the data table for addressing, if you would have clicked on the data table and dragged in I:1/1, you would have realized that it wasn't there, so you would have had to add the input module. Bit 0 is the first input or output. Remember, everything starts at 0, so the first slot in the rack is 0. The first bit is 0, which I guess is screw terminal 1. So 0 is still confusing everybody. And you can use the data table for forcing. You need to be online for forcing, but you can go into the data table, and in the data table where you normally look for 1s and 0s, you can type 1 or 0 and enable forces, and you can force directly from the data table by typing 1s and 0s into there. This is another point where some people are still struggling a little bit, and let's take a look at the options here. I got a little bit of ladder logic here, and the first 2 are examine if closed. So the first 2 examples here are rung 1. So let's take a look at rung 1. So here's an XIC contact and with a normally open. So if I wire normally open push button into the PLC and I have an XIC contact, because that's normally open, I get a 0 right here on the data table. 0 means don't change the state of this. So right now this is false. We're not going to change the state, and it's going to be false, and that light would be off. If we do examine if closed, this contact, and we wire a normally closed button in, well, a normally closed button wired into the input module is going to complete the circuit to the input module, and therefore the input module is going to get voltage, and then the input module is going to show a 1 right here, even though we haven't pushed the button because the button's normally closed. So we get a 1 right here, and we look at our contact. That means we need to change the state of it. So the state is false, but if we change the state of it, it's true. So with a normally closed button, this would be true, and the light would be on. Let's take a look at the examine of open contact. So here's an examine of open contact, and it's looking for it to change states. And so if I put it normally open in there, once again I'll get a 0 into the input module because there's no voltage coming through it. And if there's 0, this will not change state. So as shown here, it's true, and so because it's true, the light would be on with a normally open button. And this is the most confusing one for everybody. If I wired in a normally closed button to the input module, the normally closed button would deliver voltage to the input module. The input module would get an indicator light, and the data table would change to 1 right here because we have continuity through the input module. If this changes 1, then this contact XIO changes state. So here it's shown true, it changes state to false, and it opens. So if you put a normally closed with an XIO, this will open and the light will not be on. So what is the moral of the story? If you want the field device to work as it's wired, then always program normally open or an XIC contact, XIC, and let the field device change the state of the contact. You wire the field device the way that it normally would be wired and program it with an open, and it usually will work exactly the way that you want it to. You got your quiz back, and you would want to review your quiz with the instructor for any items that you missed. So the week 4 topics are bit logic, online editing, motor starting, cross-reference, memory, and scan. Branching review. We've already did some parallel branching. You're doing a good job of pulling the branching down, and it starts in, it's just a parallel circuit. Starts in as at the same point. Nested branching is a branch within a branch. Okay, and we'll take a look at some examples. Here's just a regular parallel branch where we have, this is a 3-contact branch, and we could add a 4th one here. I think it's self-explanatory, but it's understanding the parallel branch. Here's a nested branch. In this case, we have this branch here, which is contained inside of this branch. So it's a branch within a branch. And you can get a lot of crazy things going on here. A lot of ands compacted into or branches, and you just have to work your way through the logic to be sure they make sense. So some nested branch programs don't lend themselves easily to making a nested branch program. So what you have to do in this case is sometimes you have to use a contact twice. So if you look at this, this first rung says A or B or C would turn on Y. Well, this bottom one's, we've got that option. A or B or C would turn on Y. Excuse me, A and B and C. A and B and C would turn on Y. Okay. This original one up here has got A and D and C would turn on Y. Okay. So now we had to use C twice to get A and D and C would turn on Y. So we used C twice to generate this branch. And then finally A and E turns on Y, and we have A and E turns on Y. So sometimes you might have to get a little creative to generate the logic that you want, being aware that you can use the switches more than once. And the example of that was the Jeopardy game, where we had the reset button out front, and we just used that reset button on each rung because we could, and we didn't want to have some crazy nested branch that was probably not going to work. So parallel outputs, you can put a parallel around an output and turn on another output, and we'll start doing a little bit more of that. Do not put outputs in series. This O2 cannot be here. They have to be in parallel on a SLC 500. And if it doesn't support parallel outputs, some PLCs might not, well, you can just take this output and associate it with a contact. So when this push button turns on this output closes to turn on this output. And this is just a way of, I guess, kind of cascading the outputs. If for some reason this rung gets really, really busy, we're going to take a look at some of this a little bit later on in this lecture. Okay. So an output of a single instance. You can only use an output once. So I've got a no-no that I've shown here. I've got light 1 here, and I've got light 1 here on 2 rungs. You can only use it once. What does that mean? Well, let's take a look. I've used PB and PB1. I've used the push button twice, and that's not a problem. You can do that. So if you look at this, is this light 1 on or off? Well, let's look. If I haven't pushed the push button, this says that this is open and the light is off. But if I haven't pushed the push button, then this says it's true and the light is on. So would it be on or off? Because this rung says it's off and this rung says it's on. And just think about if I did push the push button. If I push the push button, then this would close and this would open, which would turn the light on, but this rung seems to say that I should turn the light off. So you're going to get confused there about whether the light's on or off. In this case, it's going to take the very last rung here and solve that, and then that is going to be what gets pushed to the output module. So this last rung is kind of going to supersede this rung here, but it's going to be very confusing to you if you have a very large program and you're trying to find out how come light 1 is not on or light 1 is off when these lights are separated by a couple of hundred rungs and you didn't realize that you used them twice. Probably use an output only once. You have a scan example worksheet, and what we're going to do is take a look at this where PV1 would turn on a light. When this light comes on, it closes the contact and turns on the next light. Okay, so let's take a look at the scan worksheet. So on our scan worksheet, what it says is when you put the processor in run mode, it basically zeroes out the input table. Okay, and so for that logic that we had just there, we're saying in this case that the push button, the input 1, has not been pushed. Okay, and then therefore, because it hasn't been pushed, we're pretty much zeroed out. We're starting from scratch here. Okay, so here's our logic again, and what it's going to do is I haven't pushed this button. So the first thing it does is it checks all the inputs. Okay, this right here, this contact is an output. It's associated with this. Okay, so the first thing it does is it checks all these inputs, and that's 0. And we haven't turned this on yet, so therefore it's a 0. And we haven't turned this on yet, so it's a 0. So everything's going to start at zeros. It's going to solve the ladder. Well, obviously we haven't pushed the button, nothing's on, and so it's going to end with all zeros, and it's going to write zeros to the output modules, which means that it's not turning on the lights. At the second scan, let's start. So a 1 right here. That means that the push button has been pressed. Okay, so it starts the scan. It zeroes everything out, and then it checks. So the input right here has got a 1 in it. Well, this right here does not have a 1 in it to start the scan because we have not updated the output tables yet. We have not solved the logic yet. So these two items here are false. So it's going to solve the ladder logic now based on this first 1 being pushed in, that we pushed the push button. Okay, and so we have a 1 right here, and it solves the logic. It's going to turn on the light. And then that light, as it continues to solve the logic, is going to make this true. And if this is true, then the second light will be on. So at the end of the scan, it's going to read this input right here as a 1, this light, and this light as 1s, and they'd be on. And this gets a 1 written, and this gets closed, or this becomes true because this has a 1 in it. Now at the start of the third scan, what it does is it basically zeroes everything out, and then it checks the status of everything. So when it checks, it's going to find that the button is still pushed. Okay, we haven't changed at the beginning of this scan. We haven't changed the output, so they still have 1s written into them. So these 1s are going to remain in here because we haven't done anything. Okay, so once again, it brooms the inputs and it checks to be sure that there's a 1 on I1, and we haven't changed these, so they're just defaulted to 1 because they're still on. Okay, and so this goes ahead and explains how that works. And then at the end of the scan, because we still have the push button pushed in this case, I guess, we have 1s continue to be written into there. Now, when we get to scan 4, it looks like there is a 0. That means they've let up the push button. So the push button has been released. Okay? So I'm going to guess right here that we have let up the input, but we haven't updated the outputs yet because we haven't solved the ladder. Therefore, we're going to get a 1 and a 1 right here to start the scan. Okay? But then after we solve the ladder, it's going to find out that, hey, this is 0 and that's 0, and it's going to zero all these out. Okay? So what you're going to do is you're going to kind of work through and see, now here's the button got pushed again, and here's the button got pushed, let go of the button again. And here are the results. So like I said, when you let go of the push button here, these have not changed states yet, so it's still pushing a 1 into the data table. Once it solves the ladder logic and it ends the scan, then it updates the outputs and it pushes 0 into them. Okay? And so once again, you hit start, and these start at 0 because that's where they were before, and it solves and everything becomes 1. You let go of the push button. These remained 1 because it hasn't solved the ladder. But here's the ladder. It solves the ladder and updates the outputs to zeros. So it's a little more detailed on how the scan is working. Bits. Bits use the B3 portion of the data table. And so when you pull up the data table where we find our inputs and outputs, you can find the bits. And so when you're working on bits and you're addressing them, I would pull the data table up and I would click and I would drag the bits over to the contacts and coils, just like we've been doing, so that you don't accidentally type the wrong bit number. And bits are internal relays that are not connected to field devices. So the beauty of this is we don't need to waste a slot, or excuse me, a terminal on the input or output card by making a fictional connection to a contact. We can use a bit, which is a fictional relay, and that can go to a fictional contact. There are 256 words of memory, and each has 16 bits. This means there are 4,096 different bits available. So if they're B3, the first one's 0/0, and then 0/1/2/3, 0/ all the way up to 0/15. If you used up these 16 bits, then you could make this 1, and you could have 1/0, 1/2, 1/3, all the way up to 115. And then you could go to 2/0, 2/1, all the way up to 215. So you can go all the way up to 255/15 like that. So that's quite a few internal fictional bits. We got a little bit of bit logic here, so you're going to watch these 2 videos to be sure you understand how we can use bits. So programming best practice. The best is to turn on outputs associated with field devices if you want to turn on the field device. Turn on bits if you want logic functions, and have the bits then turn on the outputs associated with the field devices. So what this does is it puts your outputs on a rung that you have control, that you can then have contacts open or close to turn them off and on. Whereas the bits, that's logic, and you're going to put those outputs on separate rungs because you don't want to confuse the outputs and the bits. And we're going to take look at some examples. So momentary PB1 creates memory to turn off light 2 and stays on, and light 1 stays on. Momentary 5 pushes off light 1. So we're going to take a look at this at our worksheet and see what it looks like. So we have momentary push button 1 to create memory. Okay. So what I'm going to do is I'm going to put that on a bit, and I'm going to put the bit right here. So this bit does not exist. You're thinking, hey, why don't you just use light 2, like right here. I could have used light 2 here, and then light 2 there, and then this contact doesn't really exist. It's just affiliated with light 2, and light 2 would be wired into the output module. Well, at this point, because light 2 is holding my memory, I've kind of lost control of light 2, because if I want to shut light 2 off, it might affect the rest of the program, and that's as shown here. Okay, I use bit memory, so this bit is going to close, and this one is going to open. I'm sorry, I should light 1 there. So this is going to close, and this is going to open. So when this closes, light 1 goes on, and light 2 goes off. And so, like I was saying a minute ago, I could have used light 1 here and light 1 there. Okay? But if I wanted to shut off light 1 but keep light 2 on, let's say I have another push button 5 here, I push button 5, well then this would go off. Alright? But the problem is, if I would have used light 1 as my holding contact in my holding OTE, then pushing 5 would have killed the memory. And then this third rung right here would have been affected. It would have, the memory that was holding this here, that wouldn't have been part of it, and it would have went back to its original state. So once again, my memory here, I've broken out and made the memory its own rung, and then I'm using that memory to engage these other rungs, and that way when I turn out this light 1 right here, I don't kill the memory. Thus, I'm not affecting the next rung. So an internal relay, that's what I was showing there. If for some reason there's a limitation on the number of contacts that you can have, let's say there's a limitation of 7 here, and you need a 12, well, you can just turn on the bit and then put this next contact down here as that bit. So what you've got is a big AND, 1 and 2 and 3 and 4 and 7, 8, 9, 10, 11, and 12 turns this on. But if you couldn't fit them all in the same rung, you just wrap it right here. You just kind of create like a little series where this turns on and that shuts the next contact. And then you've continued your big AND circuit. On low voltage protection. So when we talk about motor starters today, I just wanted you to remember, be aware that a PLC system is going to have a master control relay right here, and it's going to have multiple E-stops that are wired normally closed, and a start, and a master control relay. And this item here is hardwired. Okay, so you have to physically hit the start to bring this contactor in here, and this is closed. Okay, this is a real contact and it will close. And remember, once that MCR comes on, it brings this voltage down here and high because there'll be a normally open contact there. So the master control relay for a motor starting circuit will be hardwired, and that must be hit. And then therefore, if for some reason the fuse blows or the disconnect goes down or anything like this, this hardwired circuit will drop out because this memory is real, okay? And then the PLC is going to die. So we'll be doing some of that, and hopefully you'll understand that today. So we'll continue our motor starting. We talked about master control. So the E-stop we talked about is wired normally closed. We're going to explore using the motor starter for the seal-in circuit, okay? And then we're going to use the motor starter auxiliary for the seal-in, and we're going to take a look at using the overloads in a circuit. So if you take a look at this circuit right here, okay, let's figure out what is wrong. Apparently here PB1 is the start button. So I hit the start, and let's say these are true. Momentary start, the motor starter would come on. And if the motor starter comes on, that means the auxiliary contacts of the motor starter, the holding contacts, close. So if they closed, then we would have memory if I let up the push button, and the motor starter would be on. Okay? Now if I hit the E-stop, then it would go off. So I would have start, stop. So is this wired up correctly? It's not. It's not programmed correctly. An E-stop is wired normally closed. So if you take a normally closed E-stop, it will provide voltage to the input module, which will put a 1 into the input table, which will take this XIO and it will open it. It will be false. So this E-stop, wired closed, if it's wired right, is automatically going to kill this circuit. This should be programmed an open contact because the E-stop is wired closed. Let's take a look at the motor overload. So the motor overload is also a normally closed contact that opens. So it looks like this would be correct, because if the motor overload has not tripped, then it would be true, and then this would be true, so we'd be all set there. So let's say we fix our E-stop here and made this open, and then so we hit start, the motor starter comes on, physically closing these contacts, giving us memory, and now we're running. Okay. What happens when the motor overheats? Well, the closed contacts on the motor, which are 1, writing a 1 into the data table, they open, and so we get a 0 into the data table. And so this contact right here opens. The motor starter will go off. The auxiliary contact will go off. Now when the motor overload cools down, the motor will not start back up, because even though the motor overload closes, putting a 1 back in here and making this true, we've lost our memory. We would have to hit start again to get this. And this is what the lab explores today, of how our auxiliaries and how our motor overloads and our e-stops work. PLC programs have a cross-reference function similar to relay ladder logic. So the lab will show you how to create a cross-reference, because some programs are very big. If you have hundreds of lines and you have a coil and some contacts, multiple contacts throughout a 100-line, couple 100-line program, you want to know how they're related. So the cross-reference, similar to hardwired ladder logic, will tell you where the closed and open contacts are. PLC memory, there is the read-only memory, and so the read-only memory is the functionality of the PLC that is in the BIOS, and that's baked into the operation of the PLC. We can't really change it. The RAM usually represents your program, your ladder logic. Now there's a battery backup on the PLCs, so that if it goes down, your computer goes down, you don't lose the program. You don't have to have the computer hooked up to it. So basically, when you dump your program into the CPU, the battery backup keeps it it'll run without your computer hooked up to it. And so there's volatile and non-volatile. So the non-volatile is referring to the ROM, and the volatile is referring to the RAM, because if you don't have the battery backup and something shuts down, then the program is going to be gone. So the ladder logic, once again, is RAM volatile versus the BIOS is ROM non-volatile. That's cooked on a chip. Memory usage. So the memory map is the data table, and we've been getting into the data table to look at ones and zeros, and we'll be getting more into it as we start doing timers and counters and bits. The user program, that is your ladder logic, and we are doing a lot of ladder logic, and so these things here are going to be volatile because they get put into your RAM. The housekeeping memory, this is the PLC to operate. This really is an access bias. This is programmed in there, and that is the ROM. That is the non-volatile part. There's a quiz for this unit, and then for the previous unit, then a lab.